So for number 7 and 8 in the acid-base section, this is number 7 and number 8. Okay, so for number 7 and number 8, this is going over neutralization, and I believe I forgot to add that into your notes yesterday. So for neutralization, what I need you to remember is that for y'all's purposes, you guys usually only dealt with trying to neutralize a strong acid and strong base. When you get to AP, then you do the other stuff. So strong acid plus strong base yields water and a salt. All right, and when I say a salt, that's some sort of an ionic compound. That's the skeleton, all right? So when you look at the one that they gave you, which was the HBr plus NaOH, and they want to know what that makes, you're going to make water and then a salt. Now we need to make an ionic compound. So which things are we going to take? Actually, do you guys remember what kind of reaction this is? We have a pair here and a pair here. It's double replacement, exactly. So take your first two and just switch their spots. That's what I would do. All right, so if we switch their spots, we end up with that HOH, and we end up with NaBr. Do you see that? This right here is your ionic salt, okay? Okay, so the big idea here is realizing that your OH minus is always hooked up with a metal. So you're always taking this guy and putting it with the anion from your acid. All right, that's the whole idea. So the next question that they ask you is something where they give you the products. So they give you water. So I'm looking at number 8 now, okay? They give you water and some calcium sulfate, right? And they want to know now, what are the two reactants? Well, remember, you have to come up with some sort of a strong acid and some sort of a strong base, because that's the only ones that make water and a salt. So the water we know is going to get split into the OH and the H at the beginning, right? That's where the water is going to come from. You guys agree with that? You kind of see what I did with that? All right? So the rest of it is going to come from this calcium sulfate. Calcium. Who is calcium most likely going to be hooked up with? An H or an OH? The OH, right? Because calcium is a cation. It needs to go with the anion. Oh, I'm so sorry. That was supposed to be a minus sign. It's supposed to go with the anion, right? So calcium hydroxide, is that a strong base? Is it part of our B on our periodic table that we went over yesterday? Yeah. Okay, so there's our strong base. Where does sulfate go? What kind of acid is it going to make? It's just, well, yes, it's a strong one. So remember, sulfate has a -2 charge. So if we crisscross those charges, that brings that 2 down here. Okay? But this is sulfuric acid, right? And how do we know this is a strong acid? What does it have 2 or more of? Has 2 or more oxygens than hydrogens. 4 minus 2 is 2. Okay? And so that's what they want you to do on these problems. So don't overthink it. Just remember the list of the strong acids and bases that we made yesterday. Okay? So when you see something like NaCl, who made NaCl? Who makes NaCl? What's the strong base? Sodium hydroxide, good. And who makes the chlorine part? Hydrochloric acid, right? HCl. Do you guys see that? So just, that's all that they're asking you to do. That's all the thinking that they're really asking you to do for that one. Okay? All right. So strong electrolytes are things that will completely dissociate. Into ions. All right? Remember, an ion means it has a positive or a negative charge. Okay? So something like dissolving salt into water, right? If I put some NaCl and I were to put that into some H2O in the beaker, I would be left with NAs floating around and CLs floating around, just all over the place. And the fact that they have these charges, right? The fact that they have the charges make it so that they conduct electricity. So the fact that they split into that, all right? You could also have something like sodium sulfate. Let's just say that one real quick. So sodium sulfate, same thing. You're going to have the sodiums floating around and you're going to have sulfates floating around. Okay? So those are strong electrolytes. Okay? All of your strong acids are strong electrolytes. Okay? So also strong acids and strong bases. Yeah. All right. Weak electrolytes. These will be for sure weak acids and weak bases, for sure, okay? And the way you can kind of notice that, I know on your review, one of the things I give you is NH3. That is a weak base you were just supposed to memorize. This is ammonia, all right? So this is a weak base. This one is not going to completely dissociate. So I don't know if you remember when we looked at something like hydrofluoric acid, right? And when we were to put it into that water, most of the HFs stayed put, but then a couple of the fluorines kind of got away and a couple of the H's did, but not very many, right? It doesn't completely dissociate. That's what makes it a weak acid, is the fact that fluorine is holding on so darn tight to hydrogen, he's not going to let it go floating around on its own, right? So they're just like hooked up. So those are weak electrolytes. So just part of them kind of dissociate, okay? Okay, and then your non-electrolytes. These tend to be covalent things. Covalent stuff, all right? And that's because what holds together covalent things? Oh, gosh. Oh, gosh. All right, so question. Water is a covalent thing, right? Right, okay. So, is it easy to break apart a water molecule? No, right? You have to put some electricity in there, change everything up, and everything splits apart finally, right? But why do we have liquid water? Why are they all hooking up? What's in between all of these?
A hydrogen bond.
Right, hydrogen bonds, which are part of what? Intermolecular forces. Intermolecular forces are way weaker than our actual bonds. Okay? That's why stuff like sugar dissolves in water. Do you guys agree?
Yeah.
But does sugar actually split apart into a bunch of positives and negatives? No, sugar stays put. So kind of the visual I gave to somebody last period was if I put sugar in, it just breaks into more sugars. Okay? So they don't split apart. There's no positives, no negatives. If I put this, the NaCl, into the little beaker, that's going to actually split into various things with positives and negatives. Like it does not stay together. And that's the big difference here. So if it just breaks into a bunch of smaller of itself, that doesn't count. That's intermolecular forces that we're breaking.
Okay,
So no charge can go through here. Okay, so for today, we're going to talk about solubility and solution. So this is the last part of your review, okay? All right, so solubility and solutions. First of all, let's review a little bit of vocab. So what does the word soluble mean? It dissolves, right. Okay. What does insoluble mean?
Not able to dissolve.
Right, not able to dissolve. So most likely it's forming a what? Yeah, precipitate, right? Okay. So it's the idea that you're forming a solid or it's not dissolving. All right, one of those. Because we could just be asking about a compound, putting it in water, is it going to dissolve? Not all the time, right? Okay, so, all right, so insoluble, precipitate, not dissolving. When you are worrying about solubility, we're going to refer to our solubility rule. So this is inside of your periodic table, all right? And so we're just going to look at what information was given to us again. So if you notice, we got a bunch of anions over here. And so you look at whatever your compound is ending with, okay? And it goes all the way down. Once you figure out who you're ending with, you're going to read it to yourself saying, this is soluble unless, and then you look at your exceptions. Or you look at the bottom ones and you say, this is insoluble unless it's with something else. So that's what we're going to write down in our notes, is we're going to write down that little funky sentence so that you don't forget it. Okay? So blank is soluble or insoluble unless, I don't know if you guys remember, I really stressed that when we were going over this. Yes. Blank. Okay? And that's the sentence that you want to kind of tell yourself. So, the only thing that's a little unclear is you got to make sure you remember who your alkali metals are. Who are your alkali metals? Group 1 or 2?
1.
Group 1. Okay? So don't forget that. And then everything else I would say is pretty straightforward. You can find those guys, all right, on your periodic table. And just give yourself the little reminder to look at anion. Okay? All right. We're all good on that one? So you guys have a nice little list. You'll get to practice a couple of them. All right. Next thing is we had curves. Okay, solubility curves. So when you had your solubility curve, remember it's the graph that's really overwhelming. We're just going to go with one line to get the basics of it again. Okay, but you guys have a graph in your review that kind of goes over like a bunch of lines on there, and you just got to read it carefully, okay? Make sure you look at who is on the label, okay? And then you pay attention to where you are analyzing, right? So if we end up above the line, what does that mean our thing is?
Super saturated.
Super saturated. Good. What is it on the line? Saturated. And what is it underneath? Unsaturated, okay? So remember, your unsaturated solution means that you can still put some more solute into it. Super saturated means it probably needs to crank up the temperature in order to get it to dissolve in it, and then you can bring it back down. That's how we get our sweet tea. Remember, this is your sweet tea up here. This one is saturated. It's the maximum amount, all right? The other useful thing that you got to remember is this is always 100 grams of water on your y-axis, and they want to know how much solute can you put into that, okay? So you're always putting your solute into 100 grams of water. So if I want to put it into 700 grams of water, what am I going to do to my number? Right. Multiply answer by 7. And you'll have a different example in your review. Okay? So don't forget that. And then just know that this is showing temperature increasing. Okay? All right. Next thing, molarity. So molarity is the same thing as concentration. Okay? So if it has a concentration of, it's a big M or it's a brackets. Okay? Molarity is equal to moles over liters. The tricky thing, especially for y'all being pre-AP, is we won't give it to you in moles. We're going to say, hey, if you have this many grams and I put it into 4 liters, what's the molarity of the solution? You're going to divide it by its molar mass to get it into moles and then put it into the formula. So you start with this and you end with this. Okay? And this is 1 mole. Okay? So that's molarity, and then you can also rearrange it. It's really important you are in liters. It has to be liters. If it's in milliliters, remember you're going to move it 3 to the left. Okay? Yeah. Yes. Okay. The other one that you guys got in this little section was M1V1 equals M2V2. And that is for dilutions. Okay? So for dilutions, the first set was your stock solution, which is usually your more concentrated solution. And then this is your diluted solution. So typically, they want you to solve for volume. Okay? Or they would say, if I use this much and I put this much water in, what is the new molarity? Those are typically what you will solve for, either V1 or M2. And remember, it doesn't really matter what side of the equal sign you put it on. As long as you put the same pieces of information together, you're good. Okay? And the last thing I'm going to end with on this part is, please remember, polar things dissolve polar things. And non dissolves non. Okay? So what is a very useful thing that we use that's polar to dissolve a bunch of things? Water. Okay? So water will dissolve polar things. Okay? It will not dissolve non-polar things. What's an example of a non-polar thing? Soap? No, I wouldn't say soap. What? Ammonium? No. How about oil? Can you put oil into water?
Oh, vegetable oil.
Vegetable oil won't. Butter doesn't. All those fatty covalent things don't. Okay? All right. Next thing. Thermo. And this one is not going to be very long because you should still have these notes. If you've already lost these notes, then I shake my finger at you. All right. So for thermo, be ready to recognize this graph and this graph. What is this, the first graph representing? Exothermic. Endothermic. And then I am going to run you through, if you look at your review, number 3 on that last page for thermo. So number 3. For thermo, okay? Because it is a Q equals MCAT, all right? And we know that the C of water is equal to 4.18. That's something that you should just know. But this number 3 is actually asking for a little bit more. So I'm going to run you through this. You can either write it on your review or write it on the piece of paper. You'll have more space on your paper, okay? But number 3 has a situation. So what the situation is that it's saying that we have a cup of water, and I have a piece of metal that I am putting into the water. This metal was really, 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 really hot, right? So I'm going to put it into the water. What happens to the temperature of the metal? It's going to cool down. What happens to the temperature of the water? Heats up. Are these numbers equal to each other? They have to be, don't they? Hey, are you guys paying? Hey. Okay? Those have to be equal to each other, right? Whatever comes out of the metal has to go into the water. There's no other places for it to go. So that's what this number 3 is actually talking about. And it's going off the idea that I told you guys this, was whatever heat is gained comes from whatever heat was lost. And so what you're going to end up having is you're going to have MCAT for whoever gained set equal to negative MCAT for whoever lost it. Okay? It's not as bad as it looks, I promise. All right, so when you go to approach this, we need to have information basically about metal. I'm sorry, whoever gained it. Who gained it? Who gained the energy that we talked about? Water, right? So we're going to put water on this side. And who lost it? The metal. We'll put metal on this side. So all I'm going to do right now is I'm going to list out both their pieces of information, and then we'll solve it, okay? So for water, let's read this problem. It says a 0.599 kilogram sample of metal is heated to 93.6 degrees Celsius, then placed into this amount of water at 25 degrees Celsius. Temperature of the water and metal at equilibrium is 36. What's the specific heat? All right. One special part of this. When it says at equilibrium, so if you're following along on your problem, make sure you underline that. At equilibrium, that means temperature final is the same for both. Do you agree with that? Does it make sense? As this one lost it, this one gained, so eventually they have to reach thermal equilibrium, all right? Where they're both going to equal the same amount. That's all the heat that can get transferred. So when we go to do that, the water, let's go ahead and write in the details. Mass of water they gave us was 0.365 kilograms. Typically I would say convert it, but this one it's going to cancel itself out. If you were to convert it, it's 365, okay? All right, then we have a temperature initial. What was the initial or the starting temperature of the water? 25 degrees Celsius. Good. What is the C of water? It's your CP of water. I just told you up here. 4.18. Okay. And then finally, what did we say temperature final was? 36 degrees Celsius. Good. All right. Let's go through and write down our metal stuff now. Okay. The metal stuff, we have a mass of 0.599 kilograms. This is where that part's going to cancel out. The temperature initial, what did the metal start at?
25.
No.
Oh, 25. Like
It's heated to 93.6 degrees Celsius. Where does it end though? 36 degrees Celsius. Yeah, so then it'll balance it out. Yep. All right, and then the C, if you notice, is what they're asking for. They want to know what is the specific heat. Okay? All right, so when we go to solve for this, we're just going to plug things in, all right? We're going to go, and it's going to look messy at first, but all you're going to do is simplify both sides, and you'll have a number, equal sign, number, letter. That's it, and it's going to be great, okay? It'll look really easy. So we're going to put 0.365. I'm going to multiply it by C, 4.18. I'm going to oops, did not mean to write that one. Multiply it by, and I'm going to do 36 minus 25, right? Temperature final minus initial, what we did the other day. Equal to, we're going to put a negative at the beginning of the metal because he loses his heat, right? So we're going to say negative, I'm going to open parentheses up, and I'm going to say negative, or I'm sorry, 0.599 times, we have no idea what C is, times 36 minus 93.6. Okay. For some reason, this bothers everyone. Does that mean anything? Does that like mean, oh, we can't put those numbers together? No, right? We can still put those numbers together. So you're going to multiply these two. Okay? Multiply all this and make it pretty. Okay? So when you go to multiply, just for time's sake, I'm going to give you the answer. So when you multiply all of these together, you should be getting 16.78. Sorry, I have it backwards from first grade. Okay, 16.78 equals a negative, did it again. A positive 34.50, and then I have that C. Is that manageable?
Divide.
Definitely. Who do we leave alone? We leave the C alone. Divide this one over. So you're going to have 16.78 divided by 34.5 is equal to that C, which will end up being 0.49 joules over gram degree Celsius. Okay? And that gram came from the water CP, if you're somebody paying attention to your units. Okay?